Hi, this is the camera from the genome sequencer. It's a Spectral Instruments 800 series. It's a cooled CCD camera, so it's got a CCD sensor with a Peltier cooler on it that reduces the temperature to reduce noise. So it's got this fibre faceplate on the front, which sort of couples the light directly to the face of the CCD. So I couldn't resist the temptation to pull this apart. Unfortunately, I started at the wrong end, so I've done a small amount of damage, but it's certainly repairable. It's no big deal, it's just some wires that need resoldering. So if we take the front off, we reveal a humongous CCD sensor. This is about a 60mm square piece of silicon. So this is coupled by this block of optical fibre material, so this will be sort of coupling the light, and this distance will be about sort of thermal isolation. So this thing is being cooled to maybe -20, -30. We then get a temperature gradient across here, so we don't get any sort of frost or anything on the faceplate. And I think actually the heater that we saw on the camera cover on the sequencer, that might have actually been partly to just warm this up enough to avoid any issues with condensation or anything. So obviously if we just left this to sort of reach equilibrium, that some of the cold from the CCD might make its way to here, so that's probably just to provide a little bit of heating to prevent that happening. But this CCD, looking at the 800 series brochure, there is a very similar picture which says it's a 4K by 4K CCD. I got a few bits of information from a few people after the genome sequencer video, including the full manual for this camera, and also an offer of a loan of the controller card, so hopefully I'll have that in a day or two and actually be able to play with this thing. Someone sent a link to a quotation for one of these cameras. It was a slightly more expensive version because it had a cryo cooler, but that was $68,000. And somebody else who actually has purchased similar cameras, actually the slightly higher end 1000 series model, said that they're about 100,000 UK, and seemed to think the sensor was possibly something of the order of 20k, which, say, considering the size of this die, Tesla 500 commented when I tweeted the picture that it's not so much how many good die you get per wafer, but how many good wafers before you get one good die. I'd imagine this probably does have some defects. There's some mention in the camera documentation of the camera being supplied with the defect file that maps all the any bad pixels. So obviously this is definitely by far the biggest piece of packaged silicon I've ever seen. It's just insane. Now this was plugged into this board, but say because I dismantled the thing the wrong way, I should have started from the back, but obviously I didn't know that. It's mounted on this PCB, which is connected by some very thin wires, obviously for thermal isolation. So I managed to sort of rip a few of the sensor got pulled out of this board, and a few of these wires got broken off, but that's not a big deal to fix. So it's take it apart the right way and take a look at that. And one of the reasons the reason it got taken apart the wrong way was just purely the obvious way was to take the screws from the faceplate, because all the screws on here are a real pain to get to because they're in this gap. You have to sort of start them off with individually with the Allen key like that, and then use a ball driver to actually unscrew them. They're a bit of a pain because you've got sort of screws there. There's also another set of screws facing this way, so it's although it looks a fairly neat design, it's actually a real pain in the arse to assemble and disassemble. So once we get in the back, we've got this PCB here that the sensor mounts on, and this has actually got some preamp electronics. We'll pull this out in a second. So there's this central floating bit for thermal isolation. We'll take a look at that in a sec. On the back side, we have the Peltier cooler with this sort of coupling mechanism. So there's basically a copper slug in the centre. So this uses sort of spring pressure to couple to the back, to sort of press down on the back of the CCD to get sort of reasonable thermal coupling. There's some sort of greasy stuff here, and then a very close fitting sort of like sliding coupling on there. And then obviously the Peltier cooler is actually bonded with what looks like silver loaded epoxy to the back plate to get the heat out. And this is a two-stage Peltier. You notice it's got different numbers of elements on each layer. The reason for that is that the one at the back has to not only take the heat that's being pumped from the front face, but also all the waste heat from this front section, because Peltiers are very inefficient. I think they're something like 10% or very low efficiency. So although you can stack them to get improved performance, each layer in the stack has to be quite a lot bigger or have a lot more elements than the previous one. A few years ago I took apart a Peltier stack that was designed for the front end of some sort of satellite receiver sort of front end, and that had, the front CCD was about something like an inch square, and I think it was either a 3 or 4 layer stack, and the back layer was something like 8 by 10 inches with some colossal heatsink on it. They're using the same size, but they're using a different number of elements. And also there's these connectors. I'm guessing these are probably vacuum feed-throughs, and I'm expecting these to actually be basically back-to-back, sort of pin to pin, and with connectors going onto the other side. So these will be sort of some sort of hermetically sealed feed-through type thing. And there's these guide plates, so that as the thing gets assembled, sort of those engage with these assemblies on here. These are just made out of thick PCB, so obviously those go into guided into this to engage, obviously so you don't damage the pin as this thing's being assembled. And also on here there's a temperature sensor. There's 3 wires on here, so I measured it to confirm that it's a 3-wire PT100 sensor, so that's a fairly high accuracy temperature sensor. Although interestingly, it's on the Peltier, not on the back of the CCD. But as this is sort of the object of this is just cooling it down rather than necessarily going to a very accurate specific temperature, that's probably not a huge deal. It just probably made it a bit easier to manufacture. This heatsink off, in the original video I commented that sort of this looked like it was stainless steel, and someone in these comments said, well, actually it might be nickel plated aluminium, and I think that might be the case. It does actually feel fairly light for its size, and just sort of filing a little bit off, it did feel certainly a lot softer. It certainly isn't stainless. So it may well be nickel plated aluminium, and I'm guessing the nickel plating might be something perhaps to do with vacuum compatibility. But these fins have got an amazing sort of sound sustain on them. Just carries on. If you sort of give this a good whack, it carries on for like almost a minute. And this is the PCB. There's not much on it, so it's described as a preamp board. All it's got is 4 of these OPA 656. It's the 500 megahertz JFET input amplifier, so that's obviously doing the front end amplification for the CCD. We saw in the sequence of the video that there's 4 A to Ds in this thing, so this is probably reading out from the 4 quadrants of the CCD simultaneously for speed. Nothing really that exciting here. One interesting thing is they've got these massive ceramic caps. Now, because this thing is in a vacuum, they need to be a little bit careful about what components they use. So for example, you wouldn't see any electrolytic caps or anything that might potentially outgas and contaminate the vacuum. One I've seen, because this is using a fibre coupled CCD, me opening this up isn't going to be a huge issue from the point of view of dust, because the optical path to the CCD is completely sealed inside that fibre, so a little bit of dust in here isn't really going to make much difference. The vacuum is purely just to maintain some thermal isolation. And so you can see this this has been manufactured just with a slot, and then they've just drilled the corners out to separate it. It might well be that they actually where it's connected, very thin jumper wires connected across, obviously to provide some thermal insulation. The cold of this section, you're not sort of wasting, you're leaking heat from this board outside onto there. So as expected, on the electronic side, we've got these sort of connectors that plug into this vacuum feed through. This does look slightly fiddly because obviously this lifts off. There are some connections to the front, so we've got 2 connectors that go onto the board, so I need to get those off. This one's not too bad, but there's one located down there which could be going to be a bit of a fiddle to get to, I think. So on the back of this plate, once we've got the electronics out of the way, seems we've got 3 things connected into the vacuum chamber. This is the valve that opens to let you pump it down. Fortunately, it's got the voltage, that's 24 volts, so we now know what to give that when we repump this. That's just connected directly to the connector on the back panel, because obviously that's something you're only going to use when you're pumping it down, so there's no need for that to be connected to the rest of the electronics. That just goes to this connector on the back. Here we've got a device which I'm sure will be a vacuum sensor, because looking through the manual you can do a software readback of the vacuum level, and there's actually a LED on the back here. That LED lights up if the vacuum's not sufficient, so when we put this back together again we'd expect to see that LED lighting up, so to tell us it needs pumping down again. So this will actually read back the actual vacuum, so that as you're pumping it down you can look at the pressure as you go, and obviously just as a diagnostic thing. Also on the side of this there's a device which I'm sure this will be a thermistor to measure the center of the temperature of the sensor, because a lot of pressure sensors are temperature dependent, quite significantly temperature dependent. Now on the back of here we appear to have, now that says air packs I think, so I think that device at the bottom is a like a thermostat sort of switch type device, so that's probably a sort of a last ditch thermal cutout. But there's also another device on top of it which I'm guessing is probably a sensor, so it can actually measure the temperature. But there's that's also just used as a cutout, as like a safety cutout to prevent it overheating. Obviously, because you've got all the heat from the cooler coming on here, and obviously if the fan's not running, that could potentially go over temperature. And the other device, we've got this tube coming out here into this completely separate tube. The only thing I can think that would be is a desiccator to pull any excess moisture out of the chamber. And you occasionally see additional reservoirs, but the internal volume of that thing is obviously so big it doesn't need any extra volume, so my guess is that's probably full of some sort of desiccant material to pull any moisture out. And I wonder if maybe that's just held on by the cable tie, so you can actually pull it off and heat it up to regenerate it. Maybe you have to do that, but obviously I don't really know what temperature that needs. And so the only other thing, so we've got these vacuum feed throughs, looks like they're glass or something in the middle. Interesting, they look like they've actually been, it looks like they've actually been soldered in, so that might explain why this isn't made out of aluminium. So it looks like they're either soldered or brazed. Obviously they are soldering and brazing gives a very good vacuum seal, and as these are subject to quite a bit of mechanical stress, that's maybe why they've been sort of soldered rather than glued in, just to make sure they're completely solid, and disassembling it doesn't affect the vacuum sealing. These other devices look like they've been screwed in, but there's also some sealing resin, and this just goes to the back panel vacuum port. And again, something I found in the documentation, there's actually a little grub screw in there to prevent stuff leaking in if there's a slight leak, or if you just, well, yeah, for example, if you accidentally open the vacuum valve, you don't want a load of crap sort of piling in there. So this board is the input from the CCD. It's labelled 4-port integrating DDS, not quite sure what DD. It implies there's some sort of integration going on, and we've got these sort of big capacitors here which would reinforce that. It looks like there's 4 identical channels, so I think it's reading from 4 quadrants of the CCD simultaneously for speed. There's some sort of front end chips here, I don't know what those are. There's some DG611 analog multiplexers, and some load of OPA 656, which are 500 megahertz high speed op amps. So these are sort of clearly providing gain integration, whatever, to condition the signal from the CCD after it comes out from the preamp that we saw on the CCD board. Here we've got 4 16-bit DACs, so these are going to be for setting up probably offsets and maybe gain, sort of high-low points to maximise the dynamic range of the A to D converters. And we've got 4 AD9240 14-bit 10 megasample per second ADCs, and these go into this FPGA. This is a Xilinx Spartan 2 100. So it's a fairly small FPGA, so this is probably just doing things like maybe de-interleaving, perhaps a FIFO buffer, but there's certainly nowhere near enough space for this to be taking complete images or anything. That's just the configuration memory for the FPGA, and this is obviously going to be a JTAG port. Quite a lot of analog regulators on here, because of course there aren't any switches at all in here, because of course the whole point about this thing is super low noise, so the last thing you want in here is a sort of noisy switch mode regulator. There's actually a whole load more regulators down here. Again, with sort of just some large copper pads for heat dissipation. There is also a fan on the outside. Now this one's actually really noisy. This definitely needs replacing. It makes a hell of a noise. This sort of obviously is pulling air in. Then we've got some air vents on each side, just to get a bit of airflow through the through across all the PCBs. So that's sort of handling all the input stage. So this is taking the A to D data, then it's going out down to the processor board down here. You can see all these tracks coming down from the edge connector. This goes into a second Spartan 2 100 FPGA, and we've got and here there's a DSP. It's a DSP 56303, providing some sort of processing of the data. There is some mention in the manuals that the software can upload code to this, so that it can maybe do customized processing. So obviously this is a very specialist piece of kit, so different users will have their own specialist requirements as to how they want the data processed, maybe synchronization, formatting, whatever. So there seems to be some option for uploading data for this. It may also be possible to upload data into the FPGAs remotely as well, although say the base configuration is stored in these flash chips. It may be possible to override that, to download code to do some custom operations. And the data that goes into this is a Cypress Hotlink 2 transmitter chip, which drives the fiber module that you can see in here. The fiber optic transceiver module. A couple of oscillators, a couple of ports. I'm sure these are going to be JTAG or debug for this. That's probably JTAG for the FPGA. Maybe that's the debug or configuration port for the DSP. I did have a poke around there's a UART on this device. I did poke around the TXT and I couldn't see anything, but then again the camera probably wasn't actually running, so maybe there's some debug information there. Another linear reg up here. The power comes in here, so the power comes in from the back connector down onto this connector on board. Looks like there is provision for a different connector. I think that may be similar to the connector we saw on the power supply, so maybe there's options for alternate connectors on here. Say a load of common mode filters, again more noise filtering, another linear reg, a couple of crystals. That's incidentally that's 100 megahertz DSP, so not crazy powerful, but it can probably do a certain amount of processing to the CCD data. But there isn't enough RAM, for example, to do anything like deinterleaving or major format conversion. That'll have to happen at the PC end. And around here, this is the driver board that drives all the voltages and waveforms into the CCD. We've got a ton of these, are all linear regulators. A lot of these are LM317s with a whole load of adjustments. So these are obviously for adjusting lots of different voltages for the CCD. So you'd sort of, no doubt there's a very extensive setup procedure where they have like calibrated images and then they sort of tweak these with their appropriate tongue angle to optimize the performance, because obviously this is a very high performance camera system, so there's probably a lot of work goes into just manually tweaking and adjusting. So I'm sure those CCDs, there's a lot of part-to-part variation between them. And also, as obviously these two sideboards connect to the CCD, I'm sure that there are probably different variants or different build versions of these, because this camera does come with quite a few different options for different CCDs. So on here we've got a bunch of EL2260, which is 130 megahertz current feedback op amp that can drive up to 80 milliamps, and there's a load of MOSFET drivers, EL7202 MOSFET drivers. Those are pretty good driving things like the clock lines, which are quite capacitive, and so we've got all these capacitors here which will be providing that instantaneous current delivery to drive the fairly high capacitance of the CCD. Again, a whole bunch more linear reg stuff, a few other op amps, LT1114 op amps. Surprisingly, no D2A converters on here, so there's nothing that the software can set in terms of the CCD voltage. I don't know enough about CCDs to know whether you'd ever need to do that or whether you just set them all up once and then that's it. The only other stuff on here, there's a couple of opto isolators and some links. These are to do with there's two connectors here for shutter and aux, so these are for things like shutter timing, external shutter triggering, and I think probably an output for shutter synchronization. Just select whether you want TTL or isolated levels. Of course, you'd often want to have an isolated input, because again, if you want to keep all the noise nice and low, you don't really want to have any ground loops. I think they're saying VAC cal, so that's probably going to be the vacuum sensor amplifier. There's an LT1288 A to D converter here, so that's probably take signal from the vacuum sensing, maybe also temperature sensing, to digitise that so that can be read back over the PC interface. What looks like an NTC thermistor down there, great big capacitor. The resistor again, that's maybe just some limiting to burn off a little bit of power before it hits the these linear regulators perhaps. And there's a MOSFET. This is screwed to the front panel. I'm guessing that's probably the to control the Peltier cooler, either just to turn it on or to maybe also do some regular, it maybe does an on-off cycle to limit the temperature. So that's right next to this connector, which is where the cooler plugs in. The only other thing, there's an unpopulated TO92 device there, and because of where it's positioned, I'm certain that has to be an option for a temperature sensor, just to sense the backplate temperature. Obviously this one had a separately mounted one, but obviously this, I'd imagine that almost every one of these they make is customised and different in some way, so there's all sorts of different build options. And the dates on here, there's 2004 and 2005. According to the website, the 800 series is still a current model, but the pictures do look a bit different. So obviously this has probably been revised over the years. Quite a few of the chips I've looked up have come up as obsolete, so I'd imagine the current models are probably quite significantly different, probably using more modern FPGAs. Right, so I need to replace all these little wires. First thing I'm going to do is just take the old ones out, because even though some were still intact, I don't know whether some of them might have just been on the point of snapping because they've been bent. Now this is quite a thick PCB and they're fairly small holes, so it's actually quite difficult to clear holes in this situation. The trick when you're confronted with a difficult through-hole soldering situation, for example if you've got like a multi-layer board or a thick board like this, firstly is to sort of put fresh solder on all the holes, particularly if it's got lead-free on it. Give it a good reflow with leaded solder to make it flow more easily, and then actually melt it from both sides. So I've got a Metcal vacuum tool here and a normal iron from the other side, because the problem is that if the heat doesn't travel all the way through, you suck out sort of the solder on the surface and you end up with like a plug of solder in the middle or at the far end that can be very difficult to get out. So the first thing is make sure you've got fresh solder, stick some flux on it, so make sure the solder goes all the way through, because of course the solder acts to conduct heat all the way through the joint. So it's going to melt one side. I'm just going to melt one side and then suck from the other and take this iron off, because obviously that could be plugging it and stopping the air going through. That's just to make sure it's heated all the way through. So you can see now we've got a nice clean hole all the way through. And if it doesn't go first time, then instead of just repeatedly trying, put some fresh solder on, make sure it goes all the way through, because it's quite easy to damage the through hole. So it's really all about getting it hot enough. One little detail I've noticed on these boards is each of these 4 amplifiers is sort of star grounded to one of the sensor connections. Although, I mean, to be honest, I find it hard to believe that actually performs any better than a ground plane in practice. But I suppose it doesn't really cost anything extra to do apart from a little time on the board layout stage. But okay, so I need to replace these wire loops, but obviously I can't really do that with this board sort of floating around, because I'll just snap again. So what I've done, obviously, looks like the way they did it, they retained the corner tabs on the PCB panel and then drilled them out afterwards. So I've just put some screws through those drill holes to turn it back into a rigid panel. So I'm going to stick all the loops in, then sort of mount it. Then I should better then take these nuts out, drop the screws through, and there's enough space under here. What I might actually try doing is using a magnet, so hold a magnet there, take the nut off, and then drag the screw out this hole with a magnet. But worst case, there's enough space that it will rattle around. I'll just turn it upside down and hopefully get the screw out afterwards. So stick these loops back in this PC, and obviously also it'll be a real fiddle doing this wiring while it's in here. Whereas if I do it on the board, then it's going to be a lot easier to deal with. Right, so I found this is the thinnest tin copper wire that I've got, which is 35 SWG. Instead, when you're dealing with sort of thin solid wire like this, quite often it comes off the reel, it's all sort of bendy and sort of straggly or whatever. If you give it a little stretch, obviously thicker wire you need pliers, you've now got a nice straight bit of wire that's a lot easier to deal with. It also makes it a little bit more springy, which can sometimes make life a bit easier. So what I'm going to do, I'm just literally going to take length of this and then just bend it into like a hairpin shape. And I'm going to leave it. I'm going to leave the springiness in there, because when I push it into the PCB, then it will spring out and hold onto the sides, so it stays roughly in place. So we've got a group of 4 there. So I'm just going to tidy those up by just insert a screwdriver. Just push them all down. Some of those are falling through a bit, so I'm just going to solder one end and then adjust the other end to get a consistent height. Trim the other sides off. Incidentally, another quick tip: if you've got reels of sort of magnet wire or tin copper wire, obviously if you just leave it on the reel, it will sort of start unrolling and get all straggly and messy. So if you just cut a little slot into it, then you can just tighten it up and just pull that down. So that's now going to stay nice and neat and not unroll all over the place. Right, so that's all those links put back. I've cleaned off sort of the excess flux just in case of any outgassing or anything, but as I said, this vacuum isn't super critical. Yeah, for example, it's not as critical as if this was a packaged CCD with a window in front of it, because the fibre is bonded onto the CCD. Any sort of small amount of contamination in here isn't going to get into the optical path, so it isn't hugely critical. So making sure that I get this the right way round. Oh, incidentally, if you're sort of in the habit of marking things with a permanent marker, just remember, if you're then cleaning flux off with flux cleaner, the markings can disappear. But fortunately, there's some additional markings on here to so I know which way things go round. Now, the trickiest bit is just I've got to line these CCD pins up on the connector. Obviously, I can't really see what's happening, so I need to. I've sort of got to basically feel for where the connector is. And of course, I can't totally rely on these screw positions, because this board might be in a slightly different position because of the wire, those wire links. Right, I think that's seated. Let's just double check. Okay, it looks like we've got the ends of the connectors in the ends of the pin row, so just push this down. Oops, slacken these screws off a bit now. Feels like it's nicely on. Let's get those screws out. I'll just tip these screws forward so they're now stuck to this magnet. Let's see if I can find somewhere to get them out. That's 2 of them. Now, one thing I've just noticed, the vacuum seals on these, they seem to be fairly hard. I've got a suspicion this might actually be a metal seal that's designed to sort of compress once and then be replaced if it needs to be refitted. So we'll see how it goes. There is a bit of grease on there as well, but it might be the case that I might need to replace these seals, but we'll try it as it is. It's not the end of the world if I have to take it apart again and redo that, but we'll try it as is. Okay, let's try and pump this thing down. Hopefully, as I said, I'll have the PC card and software fairly soon, so we can actually look at the figures from the vacuum sensor. But I think we're trying to do an initial pump down on this. This is my old Edwards E2M5 vacuum pump that I bought a long time ago, primarily because it was really cheap, with the sort of intention of getting into like neon type stuff, but that was probably 15 years ago, and the only thing it's ever been used for is when I needed to move my air conditioner outdoor unit to pump that system back down, so at least it's going to get a little bit more use. I've got sort of an improvised arrangement of various sort of tubes and fittings out of my box of random pneumatics things. This is the manifold I bought when I had to do the air conditioning stuff, so that's just going into sort of various random bits of tubing to fit the port on the camera. One nice thing about vacuum, as opposed to pressure, is that it tends to suck itself sealed, so you don't need to worry too much about sort of super sealing everything, because the vacuum will actually often do it for you, but you just need to make sure that tubing doesn't collapse and seal itself. So we just turned it on, we see we've got that vacuum yellow LED on, indicating there's a problem with the vacuum, so just start pumping this down and hopefully that will go out. So we've got a little bit of a vacuum. I'll now open the valve, which should increase in pressure. Yeah. So if I now open the valve to the pump, so that should be pumping that out. I'll leave that running for a while and see what happens. Okay, now that LED's not coming on when I turn the power on, so that's a good sign. Well, I've had a bit of a poke around with the scope. I can't see anything happening, so it looks like the thing's sort of in a dormant disable mode. That might be because it's not seeing the communications link from the PC. Instead you can see the laser. That looks fairly red to the eye, but obviously it's actually infrared, so it's going through the camera's IR filter to produce a weird colour. The only thing I have noticed is that if you switch it on initially, the this bottom right hand LED for the cooler is off, but if you turn it off then turn it on again fairly quickly, it then comes on, and the input power to the power supply goes up from about 60 to about 150 watts, and this plate does start getting warm. So I don't know whether that's just some accidental feature or some deliberate way of just some way of forcing the thing to turn the cooler on from power up. It's also conceivable that the camera doesn't actually start up until the cooler's down to temperature. When the thing's running, it will be producing probably a significant amount of heat. So if you turn the CCD on and then turn the cooler on, then the cooler is going to be fighting against the CCD to get down to temperature. So I might just leave this running for a while just to see if it does anything different. Another thing that just struck me, looking through the manual, it does actually make some mention that this has got an internally squared prompt for configuration. Now, I haven't actually seen that. There's quite a lot of info, so I doubt it would be sort of one of these little SOT23 jobs down here, but it's possible it could be this. This is an Atmel flash, which I sort of assumed was probably the DSP code, but actually the data lines do seem to be running into the FPGA, So it perhaps could potentially be being used for storing sort of non-volatile data and config data as well. Can't really tell. Don't particularly want to take that off just to read it, at least not until we've exhausted any other avenues. Probing the TX pins of this fibre module doesn't really reveal anything. It just seems to be a pretty static sort of blank carrier type pattern. So we can see this sort of fairly blank pattern, no obvious data. Looks like the symbol rate is about 1 gigabit per second. And I've just noticed that this vacuum valve LED's coming on now, so I think we maybe do have an issue with those seals possibly needing replacing to maintain a vacuum. Right, so although the vacuum LED was on, it did still have some vacuum, but clearly it had been leaking because that vacuum LED was starting to come on. Just taking this apart again, so this is the type of seal. It looks like it's a metal tube which is designed to crush when it's sort of compressed like this. So it looks like the inside sort of folds inwards and it compresses, but obviously there's no springiness, so that's clearly a sort of compress it and then it's done type thing. Feels like it sort of might be aluminium or something. If anybody knows, what this specific type of seal is called or what it's likely to be made of, please let me know. What I'm going to do in the interim is I'm just going to stick some standard rubber O-rings in here because they should provide a reasonably good seal, although possibly might not last quite as long. And so if someone can maybe point me to some sources of this proper seal long term, it'd be good to get hold of those because I've done a bit of web searching and there's zillions of different types of those seals, whereas the rubber ones I can just get easily from eBay. This has also got some sort of grease on it, which may well be special sort of non-outgassing vacuum grease. So I found someone that sells tubes of that, but it's about sort of 15 quid. So maybe if someone uses this stuff and can just send me a small amount of it, that might be useful as and when I get hold of the proper seals. But so I think the rubber ones will probably do, at least to the point of seeing if this thing, I can get this thing running and see if I can find anything useful to do with it. Okay, so I've got to wait for those O-rings to turn up. Hopefully tonight I'll be picking up the interface card to borrow to have a play with. But this video is getting fairly long and I've got something interesting coming from China hopefully tomorrow, so that might delay further playing around with this thing, so I'll do that as a part 2. Hopefully we'll get this thing up and running and figure out if we can actually do anything interesting with it.